the last talk in the block on Epsilon Aurigae with Gary Cole developing a polarimeter to support the Epsilon Aurigae campaign. Gary.
Thank you, Brian. Good morning, everyone. I'm going to try to avoid all jokes since mine are worse than pretty much anyone else's. All right. This project really got started here at SAS last year. I have been dabbling with polarimeters for quite a while, but I walked up to Dr. Bob and said, do you have any interest in polarimetry, Epsilon Aurigae? And got this very positive reaction. Some of us who had experience. Anyway, about a week later in the mail, I get a copy of a thesis from 20 years ago on the last eclipse of Epsilon Aurigae, and which showed a great deal of polarimetric measurements. And I said, well, it looks like something I could do, so I'm going to try to make an attempt to do it. Now, Epsilon Aurigae is a very nice target for small telescopes because it's nice and bright. And that also makes it practical to do polarimetry because polarimetry needs exceptionally a lot of light in comparison to many of the other things we do. Now, I have tried this technology before. I started a poster here about 10 years ago on an attempt to turn an SGS spectrograph into a spectropolarimeter. And I built 2 more instruments myself over the years. So I figured the 4th try would be a charm. I could actually end up with a production design. And I decided the secret was to actually copy somebody else. So there was a paper that came out about 2 years ago about a development on the 88-inch in Hawaii, and I sort of slavishly somebody copied their design. So, and that proves to work, which is an excellent technique. I recommend it. All right, what's polarization? Without going into the math behind this, which I would be ill-equipped to do, fundamentally, any time that light hits something, scatters, it tends to become polarized. However, we don't tend to see this very much because in most cases that polarization is in some sense symmetrical and just cancels itself out. However, if you've got a jet, some kind of symmetry, something moving across your face, for example, you may well see that polarization signature come out as a measurable event. And that's what we're basically looking for in terms of Epsilon Aurigae, is as that disk crosses, is something going to happen? And when we looked at it 27 years ago, at the exit cycle, there were some fluctuations, which had no other apparent cause except they happened in the polarimetric data. Now, we also see polarization from interstellar dust. In fact, that's how interstellar dust got discovered, because of magnetically aligned silicates, basically. And that is the dominant effect you see. So when you talk about a star having a couple % polarization, that almost always is, in fact, caused by the interstellar dust. And any sort of local effect tends to be a small magnitude on top of that. So we're dealing with fairly subtle kinds of phenomena here. Okay, so the essence of the problem is you want to measure a weak signal against a relatively strong background. Okay, polarization can be defined as typically as an ellipse, and you're interested in the major and minor axes, their magnitudes, and the orientation. And all that can vary as a function of what's going on at the star. In order to measure that, you basically have to take 4 cuts across that ellipse, and you can do that with 4 Polaroid filters. You can do it with rotating crystals and several other techniques I'm going to show. There are basically 3 ways to do this. Now, that's a super simplification. If you go in the literature, you can find about 150 examples of polarization instruments. So I will make no attempt to try to explain them all, but fundamentally there's 3 techniques. The first is literally you just put Polaroid filters in your camera, take pictures of the object, and then subtract the images. And any difference in the brightness will show up as some sort of a interesting pattern of activity on the front of that object. And this is particularly obvious in things like the Crab Nebula. That just put Polaroids in, and you see this wonderful effects where you can see the strongly polarized flows of material inside that. Unfortunately, this doesn't work very well for stars, because the effect we're looking for in stars is a lot smaller, and the varying PSFs between these images and shutters and scintillation and everything else just makes it really hard to subtract 2 star images and end up with a number that you have much confidence in. So the technique that was dominant in the scientific community up until about 15 years ago is essentially one of modulation using photomultipliers. So through a variety of variations of this, essentially you put a Polaroid filter with a motor in the starlight, rotating very rapidly to beat scintillation, run it into a photomultiplier, and then demodulate it to get essentially a magnitude and a phase angle. And this is a very high precision technique, which was used widely for 20, 30 years, from the invention of photomultipliers up until the mid-90s, basically, when the CCD era came along.
How rapid?
20 times a second, maybe faster. Some of them 60 times a second. Very rapid modulation. Because you're really trying to beat scintillation, is the problem. And you need a lot of light, of course, to make all this work. The third technique, which is what I'm using, and which is, I think, essentially the technique today in general, is what you can refer to as a differencing or differential polarimeter, where you take light from the star and run it through something which will split it into two alternate images of opposite polarization. And calcite isospar does this naturally. It's been known for several hundred years to do this. And so it's pretty simple. You just, starlight goes to crystal, out comes a double star. It's great. Look through an eyepiece with it. It's wonderful. You know, double stars everywhere. Here, what you measure, basically, then after taking your image, is you simply measure the relative brightness of those two star images. And that's just photometry. So it's something we're all familiar with, preferably at the highest possible precision. Now, you then rotate this crystal around to take another cut, so to speak, of that incoming light, and get another pair of images, and ratio the two of them, and now you've got essentially the polarimetric signature. Now this is a great technique with just a few minor limitations. It's great because scintillation, shutter timing, clouds, none of this affects it because the light hits both images exactly the same. But it does hit different pixels. And as we are very aware collectively that it's very hard to calibrate pixels to 1/10%. So this becomes somewhat limited because of the fact you get a variation of where those two images hit. And also, if you've got this maybe a ½ inch or an inch thick crystal, you've got field variations of light being thrown around by the crystal, which are pretty much unavoidable. So the solution to this, which was started being used in the mid-90s, if not a little sooner, is essentially to use a wave plate. That is another piece of birefringent material which will rotate the plane of polarization when it is physically turned. Now, this wouldn't work if it was 3 inches thick. But fortunately, there are some materials, in particular polymer materials, which are very, very thin. Let me go backwards here. Which are very, very thin and can do a very accurate job of rotating the plane of polarization. And that's the particular mechanism that they use with the Wyatt telescope, and I had used about 10 years earlier, and so we did with this one. So essentially, you just put this wave plate material, so the half-wave retarder, into the light path, and then rotate it to several fixed positions. And that has the effect of switching the polarization. It's hitting the crystal, and then you're using the same pixels on the back of the camera. Now, that fixes scintillation, that fixes lots of stuff. Sorry. We're using the same pixels now, so we solve most of those problems. We are beating the flat field problem because that wave plate has essentially no effect on the flat field image. And the strongest feature here is that you can swap 90 degrees. So you have 0, 90, and you can literally flip it to 90, 0, and by ratio of ratios, you flat fielded out all the pixel variation. So you've ended up with essentially a perfect CCD without even trying. So that's a really good feature, and there's really no other way to do this. Okay, now, this is almost perfect, but not quite. First of all, there's no such thing as a perfectly achromatic retarder over the entire range of electromagnetic radiation. But they're pretty good. The one I'm using has less than 0.5% variation between 400 and 700, and only about 0.75% out to about 750. So most of the visual range is picked up by this retarder with very little error. And the people that did the Wyatt work did a study on it and showed that the actual errors induced by the limitations of the wave plate were down in the 100th of percent range. So really not an issue here. But you still got mechanics, and that always adds a certain opportunity for variation. you've got a telescope, you're looking through the atmosphere, it's bouncing around, so there's, you don't quite achieve the perfection you might get from a desktop study. But the real issue that drives you is that photons are finite. And that is what really makes this a little bit different from typical photometry. Typically, if we're looking to do 1% photometry, then we're absolutely required to get 10,000 photons. Hopefully a few more, but at least that, just from Schottland's point of view. But to get to polarimetry, where the desired error level is 1/10% or better, we're now immediately forced to go to 1,000,000 photons. And that's about 5 magnitudes. So any telescope that can do 14th magnitude photometry well, filtered, probably is 9th, 8th, 9th magnitude polarimetry. Very considerable loss. It's about the same as trying to do medium resolution spectroscopy. About a factor 100 in light. Okay. So you need a lot of exposure. Okay, well that's fair. We just sit on the star a little while. But there's another problem, because CCDs do not have infinitely deep wells. In fact, the best, our cameras typically have 100,000 electron wells, something like this. So perfectly focused stars will simply fill the wells immediately, and you'll never get anything like a few million photons. So the solution to this, basically, is to seriously oversample. Now, there are oversamplers, and there are oversamplers, and then there's me. We're talking about taking the light and spreading the core of the light over, say, 50 pixels. It's really defocused, almost to the point you see a hole in the middle of the front of the star image. Okay. These are blobs being aimed. But it allows me to get very high signal levels, which is really the objective is. Now, it also turns out that these Savart plates, these glued calcite crystals, have some natural astigmatism. So that rather than giving you a perfect airy disk, they give you a perfect little ellipse. So you can't quite do circular photometry on them because, in fact, they don't have circular images, even in the best of cases, without my help with the defocusing. Now, telescopes. There's one little problem with telescopes. Anytime you run light through a right-angle mirror, it becomes polarized. By about 5%, maybe more. So it depends on the coating and the surface of the dielectric layer. You can get up to 10–15% polarization here. So telescopes that use complex right-angle mirror structures, like, for example, Newtonians or Naismiths, just disastrous from polarization point of view. What you really want is a nice, simple Cassegrain telescope, which we, of course, have a lot of experience with. The other thing is that your limitation on precision is not really anything to do with the size of the telescope. It's really just a question of how deep you can go to get that million or a couple million photons. So that's helpful in this case. Which means a small telescope can do essentially the same level of precision as a much larger one. And you don't need great optics because, well, you're fixing that even if you had it. Okay, so here's the instrument I've done. Very straightforward stuff. It's a CA with some optic fillers, Astronomical photometric fillers behind it. Then this polymer wave plate, which is a very, very thin piece of plastic, is mounted on a ring gear structure controlled by a servo motor. So it can be stepped into several positions in order to do the analysis. The light then goes through a luminance filter simply because the wave plate is rated 400 to 700. So I just took a very conservative rating and chopped it with a luminance filter, which hits the exact range. So my B and R ranges are actually slightly constricted. And then it goes into this calcite plate, which is right in the throat of an old ST6. And ST6, by the way, does not have E improvements. It doesn't have micro lenses, but it has really deep wells. And that turns out to be quite handy. It also very slow download times, which is not exactly a feature. Okay, so that's the instrument. It's really not the biggest assembly job. You can see over the upper left here, that's the crystal sticking down inside the nose of the ST7, a little octagonal thing in there. This is the wave plate assembly, which is essentially a servo motor, which is controlled by a little controller called a fidget, which you can buy online for about $79. It's a USB device. Here's the whole circuit board, about the size of a piece of gum. Just hangs on top of this little motor. The motor drives a spur gear drives a ring gear, connects to a pin into a retaining ring, which is where the wave plate is simply glued onto. So relatively simple assembly. And there it is. It has a very long, fancy name, but it actually works. And it's hung literally in papoose fashion under the front of my C14. So it's a dedicated instrument for this purpose. So this finally came up running in an automated fashion at the beginning of November. So the data I got is from November through February when the weather went out on us. Okay, automation is really the job here, and you'll understand why in just a moment. The process we use essentially is first acquire the target and get the C14 auto-guiding for it. Then we set the filter, we take a full frame, we find out where this double star pair is, because of course we've got differential fluxure between the two telescopes. We locate it, recompute the exposure, because we want to get an exposure close to maximum but not saturation. And then define a subframe around where this subimage is. We then take the waveplate, move it to the 4 standard positions, and this is classical polarimetry right out of the textbook, of 0, 45, 22.5, and 67.5 degrees, which corresponds to those 4 nominal 0, 45, 90, and 135 cuts. And take these short subframe images, monitoring the actual brightness, so that if we get saturation, we then reduce the exposure and restart the whole sequence. And that's all done in real time as we go through this. We then repeat this entire sequence 3 to 5 times to get essentially a statistical set of data for it. So there's a fair amount of software involved in doing all this. And then we read the other filters. So sitting on Epsilon and Aurigae takes about 40 minutes to go through this whole sequence of data collection. Here's what you get. Here's your image of the single star, which comes out as a double, as seen through the C8. And then we get our 4 images with the 4 different waveplate positions. These each have a ratio, which we ratio with each other. Here's the ratios, and those then are used to calculate the magnitude of the polarization. And in this particular case, those images are a 2.5% polarized star. So you don't see it visually, you really have to extract the data and do the arithmetic to see it. Now, one of the things that you learn when you try to do this is you quickly find yourself an awful lot of files. We're talking 50 image files for just one measurement of one star. It gets out of hand very quickly. And I thought the conclusion, I just couldn't keep track of it. I couldn't put them in a directory because I was retaking images, so the naming conventions were getting complicated and so on. So I needed to find some solution that would let me keep the situational data about the weather and everything else, all these files, deal with the retakes, and let me reprocess all this stuff because I was essentially developing the reduction software as I was going along. And I came up with this real simple-minded solution I call an observation index, which essentially is at the beginning of the observation, that's a session target instrument, I basically create a little journal file. And then as the observation proceeds, I update that journal file with each new exposure, tying it to a keyword. So just like a Fitz header is what it ends up looking like, along with any commentary data that's coming out of the analysis programs or the real-time intensity checks, logic, and so on. And then also the final data that comes out of the reduction code. So I have one little text file, essentially, maybe 100 lines long, from which you can regenerate the reduction as much as you want, and you know exactly which images went to which, where, and when. And that includes flats that came out of a flat library, and darks from dark library, and all these things that otherwise hard to trace back where did you get this one from.
Text file?
Just a text file, yeah. Just update it with appending one line to it each time an exposure is taken. So it works very simply. The reduction code then just uses keywords, and we just have the convention that the latest instant of the keyword is the valid one. So if we've retaken the shot, it doesn't matter. We just get the final one that we need. Okay. The reduction process I wrote entirely from scratch because I wanted to do all this in real time. So basically, we take these dark subtracted images, we find the centroids of the 2 stars, essentially do a dynamic extraction because we've got temperature variations on the telescope, we've already defocused, this blob size is changing over the night. So I do essentially a dynamic boxing to optimize the signal-noise ratio, do a lot of data rejection, and then generate reports in real time, basically, from that, including some trace reports of every pixel we looked at and how bright it was and so on. Now, the real issue with a one-off instrument like this is how do you know whether it gave valid data? Okay, it's very possible it might not. So there's basically three kinds of calibrations. First, to try against zero standards, that the stars we know aren't polarized. Second, to try it against known standards and see if you get the same result. And third, a very simple test to say, does the wave plate work? Which you do by putting just pure polarized light in, rotating it, and seeing what the maximum difference you can get between the bright star and the dim star. And if that's a high difference, you know that basically you have very little crosstalk and you're really measuring what you think you are. Back in the mid-70s, in a very seminal book that was published at University of Arizona Press, Sierkowski basically published a set of standards which are still used for checking out new polarimeters today, I found through the literature. There's 15 very bright stars, between 4 and 8, which have very strong polarizations. It's all interstellar, so it's likely not to be changing over time. And 35 more stars, also relatively bright, with what are believed to be zero polarization, as best could be measured by the instruments of the time. It tends to be about 1/100%. So these are good standards. So here's what I got for a couple of the zero polarization stars. Now the way you do the arithmetic in this process, to calculate percent polarization, there are no negative results. So any noise in the system creates a positive polarization, even if there was none actually being measured. So I'm saying about 1/10%, which is typical. That looks like the noise floor of the system, basically. For the known polarized stars, we have two examples here. HD 43384. This is a 3% star, and I'm basically getting 2.994 kind of numbers, essentially right on target. Another one here is nominally 3.5%. I seem to be getting about 3.4. On the other hand, the standards are only plus or minus 1/10%. So what this says basically is you've got relatively little depolarization. So these are my results basically, that the extinction, that is the wave plate rotating with the pure light, got so strong that my software can't find the dim star. And I look at the image, I can't see it either. So basically, it's perfect for all intents and purposes. The zero standards look like they typically come in about 1/10% with random distribution of angles. I can't find any instrumental polarization through this process. If there is any, it's down below 25%. And the standards look good. Basically, I haven't seen any exceptions to that. So here's the data flow. Essentially, there's an automated sequence that starts with the control of the instrument. The acquisition strip then writes the file names and any other notes it makes into this OBS index file. When that filter is processed, we then call the reduction process. It goes, finds all its files, pulls flats and so on, and then generates an essentially detailed file for that particular filter measurement. Updates a summary file for that object. And then we go on to the next filter of the sequence. And then that feeds to a graph process which updates the website. So essentially we're doing direct Sky to web here for what it may be worth. And this is Epsilon Aurigae. This is 20 nights, about 50 measurements, each about 15 minutes or so long, which shows essentially that it is not changing. That's the best interpretation of this, about 2.3%, very consistent. And no, I probably could have just taken this dot off the chart and I'd have to explain it. But I don't know what that is. It was an extremely cold night. It may have been we just had some mechanical problems on the telescope. Anyway, consistent data through, this is November 4th through February 2nd. And that's what our weather window was. So, in summary, you can actually do this with obviously a very simple small telescope. You do need to have a cascade system, so it pretty much needs its own instrument for all intents and purposes. There's lots of targets. This one can reach down to about 9th magnitude, although now you're out to hour-long measurements, so you don't want to choose them lightly. It took me about 4 months to go from first light on this thing to the point where it was doing automated reduction. So there's a fair amount of software to get this whole thing to actually work by itself. It's run about 300 cycles to date, and we have 2 more years of eclipse. So as soon as it reappears in the northeast, this will be back on it every night. So thank you very much.
Question? Rod?
Gary, you mentioned light buckets and these big fuzzy images.
Mm-hmm.
So would you recommend
you want to go below 9th magnitude, sounds better and better.
Yeah, but you still got to stay on the star. You know, this flat fielding technique doesn't fix everything. You still need good tracking and guiding to keep the stars in the same positions on the chip as you go through these exposures. Yeah, at least. Sir? There are objects that show very strong polarization. Yeah. Okay, but not very many. Okay. But not very many. So the strongest signal you ever see in Sorry, apologize. The strongest signal I know that you see in stellar objects comes in magnetars. And there you see polarizations of 20% or more. So that's good strong signals. And Crab Nebula shows that kind of signal. The retarder, which is a polymer made by a company called BV Optic in Colorado, has anti-reflection coatings on it. The calcite does not. And there are definitely reflections coming off the front of that show up in the flat field. Dr. Bob? Sir?
Well, first of all, wonderful results. As you mentioned, Kemp and Henson from last eclipse reported variations on the order of 0.2%.
Right. Mm-hmm.
And in your results graph, there's a hint of some long-term curvature.
Yep.
Do you think that's outside of your errors?
I think it's outside of the errors. Whether it's real, I don't know. I've got some data from last fall that's not in there because the automation wasn't fully running. So I'm going to go back and look at that and see if there's anything that shows up in the earlier stage of the eclipse. Thank you.
Very quick. Have you thought about using photon counting? I know that's old technology to get rid of the large photon count.
You've got bazillions, right? Well, that is just that. I don't have one. Okay. You know, if I had a high-speed photomultiplier and knew enough electronics to make it work, I think it'd be a lot of fun to try that. It still gives probably higher precision results than most of these CCD photometers do.